So, good evening, students. So today we will start our week 7 tutorial for this course, Introduction to Thermal and Statistical. So for today's class, uh, we will be mostly discussing the problems that are based on partition functions. Okay. So the problems. So today's topic of discussion will be on partition functions in statistical mechanics. Okay. So, little bit about the introduction of partition function and all. We are basically discussed in the previous classes also. So, in this class, we will be doing it in much more rigorous way actually. So, let's start from the question number 1. So, this will be tutorial 7. Okay. Tutorial 7. Okay. So let's discuss the topic of this tutorial. Okay, so question number 1. Partition of a system is represented by exponential a to the power 3 e to the power 2 and to the power 3, where a is a constant, where a is a constant. Calculate average pressure of the system, average pressure of the system given A is Boltzmann constant. And the options are 4 A by 5 by 3. Option B is 2 AB by 5 by 2 square. Option C is 2AB A to the power 3 by 2 square. Option D is 4AB A square to the power 5 by 2 square. So these are the 4 options given. So basically partition function given, so from that you have to calculate the pressure. Okay. The first thing is, so what is basically a partition function? Let me just display, write a definition of this partition function once again. Okay. So let's so first write. So first, what is basically a partition function is? Okay. So let's consider a canonical ensemble. Canonical ensemble means that all kind of the NVE, or between all possible combination of the same system, the NVE will be same on all the possible combination. Okay. So Combination means all the possible microstates. Basically, NVE is conserved. Okay, so so for a canonical ensemble, uh, let's suppose the condition of canonical ensemble is in thermal equilibrium with temperature T. Okay. Now, given the fact the probability of the system is in micro state I with energy EI is EI equal to E to the power I by KBT by C. Okay. So basically it's like let's suppose these are all microstate. This is microstate 1, this is microstate 2, this is microstate 3, this is microstate 4. So in the system, in a given macrostate, there can be multiple number of microstates are there. Okay. Now, what happens is like each of the microstates are like E1 energy, these are E2 energy, these are let's say E3, these are let's say E4. So out of all these microstates, let's runs up to K. So so for all of these microstates that are exist for a macrostates, what is the probability that the system will end up with the ith microstate with having the energy EI? So the probability is basically given by this formula, PI. Okay, PI is this. So this is the PI. So now here Z is called the partition function. Okay, so here Z is the partition function. Okay, but Z is summation over all the states. I is the index. Okay, that means the summation is doing over the I. So e to the power I by kBt. This is basically called the partition function. Okay, and using this partition function, we can calculate many thermodynamical properties. Okay, now, so in our problem, we are basically asked to find out the energy, pressure actually. Okay, so how to do that? So, uh, so, hmm, okay. So we will start. We will start from the free energy. Okay. So let's start from the free energy. So, hmm. So, so first we will be writing the Helmholtz free energy. Okay. So the Helmholtz free energy is defined as F, right? So the expression of F is F equal to T minus Ts, where E is basically the average internal energy. Okay. S is the entropy and T is the temperature. Okay. That you already know. This is the basically the expression of free energy in equilibrium. Okay. So now what you do? Now let's suppose in the system there are several energy steps. Okay. 1, 2, 3, ek like this. Okay. Uh, so now in this system, okay. So what is the probability that the system will be in EI? Okay, you already know, right? This is the probability. This is the probability, right? So now, for this case, so E of EI will be in that case e to the power EI by KBT by Z. So now this is the probability of being in ith state. Now the average energy E will be summation over I EI PEI. Okay. So that will be, that means summation over EI e to the power EI by KBT by Z. Okay. So now, so this is it. So now we can write it like this. This thing we can write it like this also, right? Delta E, you can rewrite this like this. Del. So beta of ln Z. So if you do it, you can see. So del beta. So del beta of summation over I e to the power E by E into. So beta means here 1 by kBT. Okay. So e to the power ln Z. So ln Z means ln of e to the power minus E beta. Okay. So if you do the derivative, then you will get so this will basically gives you del beta. So beta. So there is a summation over here also. So summation is there. So it is equal to beta. Then you again. So this is the first. So this is the first term. Second term, you will be getting EI outside. So the power minus EI beta. Okay. So basically, you are getting that this term. Okay. So whatever you have done here is actually correct. That means, so because if you do the derivative, you will just basically give this term. Okay. So this thing what you have written here is correct, right? So now the next step. Okay. So this is it. Now the next step. So E is the average energy, which is this basically. This is basically the average energy. Okay. So now we know the S also. Okay. S is basically nothing by the KB PI ln I. So so this is basically the entropy of the system. Now we have to just substitute this all this thing into the expression of the free energy. Okay. So Now, before doing that, just substitute the values of EI here. Okay, so EI will be AB summation of e to the power EI by select. And again, if you take the log of EI, this will gives you basically minus EI by ABT minus ln z. Okay, so basically what I've done here, so log of, if you do the log of EI by e to the power EI by beta, you can write it like this, right? Uh, Log of, you can write the write this log into addition of two terms, right? Like this EI plus e to the power of 1 of e to the power EI by beta. Now the same thing, you can write it like this also, right? So ln of EI is this and ln of EI is this. So this is how we can get this term. Okay. So this is it. Now, hmm, okay. So now, we can write S as E bar by T plus KB ln Z. So how this E bar by T is coming, because the E bar is already calculated, right? The E bar is basically this thing. E bar is this thing. So we have substitute this E bar thing. So this thing is E bar and this thing is the same. So we can write it like this. That's why, because this whole thing is basically the E bar, right? So this whole thing is basically E bar, right? So that's the thing I've substituted here. And KB basically cancels, so T is there. And rest is this KB LNZ. That is minus minus become plus, right? So this is okay. So now the next, so we got the S and we got the E also. Now we have to substitute it here. Okay. So the substitute in the expression of F. So F will be minus del del beta of ln Z minus T of mod E by T plus AB ln Z. So now this is the whole thing. So now we can write it. So basically what happens, so here this is basically the E bar, right? So E bar, let's see, this should be so now what happens over here, this would be E bar minus E bar minus KBT ln Z. So now E bar will be cancelled. So free energy will be minus ABT ln Z. So this will be basically the expression of free energy. So now, now you also know that F equal, let me write it this, F equal to U minus, sorry, E minus TS. and you already also know that u d dq plus dw, right? So you can write it like this. So d equal to d minus tds minus sdt. So d is nothing but dq plus dw minus tds minus sdt df. So df we can write dq, you can write it tds, and dw we can write pdv, right? Minus tds minus sdt. TDS will cancel. So TF will be PDV minus SDT. So that means, sorry, I have written it wrong actually. So here dq is du plus dw, right? dq is equal to du plus dw. So du equal to dq minus dw. So that means there's a minus sign will be there. Okay. So sorry, so this will be minus sign, minus. So that means P would be del F del V at constant temperature, right? This will be the expression of the pressure. Okay. So now we have to substitute the F. So because in the end, in the problem, we have been asked to find out the pressure term, right? So so the pressure, so we can write it like this. So is nothing but minus del of F. So you can write it like del V of minus of ABT ln Z. Okay. So now pressure is minus 1 plus del V of ABT by ln Z. So pressure would be ABT del V of ln Z. So now, okay, so this would be the final expression of the pressure, okay, in terms of partition function. Okay. So how we have done that? We have first write this probability of energy EI in terms of partition function. Then from there we have first calculate the free energy. Okay, because we have done, we have first calculated the internal energy, and from there we have calculated the free energy. Here you can see this is the expression of internal energy, and from there we have calculated the free energy. This is minus kBT by ln Z. And also we can write the differential from a free energy, the pressure. Pressure is nothing but the del F minus del F del V at constant temperature. Okay. So this is the pressure term. So now we can get the pressure term in terms of partition function. Okay. So how can you use that? Okay. So in the problem, what is mentioned? So the problem itself, the partition function is given this. Okay, Z equal to, the problem it's written as Q anyway, and I can use our own convention notation. AQ by TH by AQ by VQ. Okay. So now E is so Z is this. So now ln Z. So first in order to calculate the pressure term, first have to calculate the ln Z. ln Z would be ln of exponent AQ T to the power 3 by 2. So this would be simply AQ T to the power 3 by 2 with. Now it gives you del V of HC to the power 3 by 2 with. This would be simply gives you 3 V square AQ T to the power 3 by 2. Okay. So this would be the pressure term. Okay. This option is given. No, so let me check it once. This one. 3. Okay, yeah, this would be the answer we are getting actually. Okay. C. Not. I think there is a mistake in the problem. Something. Okay. Okay. Is there? Anyway, so this should be basically the correct way of doing this problem. Okay, so let me just describe it all over again. Okay. This was what basically the problem is. We are given the partition function. So from there, you have to calculate the pressure of the system. So first, I have discussed what is the partition of function is. So this is basically the probability of a system that is in a high energy state EI is given by this probability. And here this normalizing factor Z, this is basically called the partition function. This is summation over all e to the power EI by kBt. This is basically called the partition function. And now, in order to find the pressure, we have to first get an expression of pressure that is dependent on the partition function, right? So in order to do that, first you have write the free energy. Free energy, you can write this in the expression of free energy. You can write this internal energy terms in terms of the partition function. So to do that, you have calculate the average energy, internal energy, that is energy at EI with probability PI, that basically gives you the average internal energy. First you have calculated this and you have got this as the average energy. Then you have written the expression of the entropy here. So this expression is basically comes from the Boltzmann law actually, that is S equal to K ln sigma or sorry omega. Omega is the number of microstates. Okay. So from this Boltzmann law, actually this formula of the entropy is coming in terms of probability. Okay. So now we have expanded all these probability terms in terms of the partition function. Then you get this big expression. Now you can simplify this thing as internal energy, average internal energy, as we have already calculated the exact form of the average internal energy. And after substituting the value, we are getting this, and then we have cancelled that E, and we are remained with this expression of the free energy, that is minus kBt ln Z. Okay. So now we know the free energy, and also we know the pressure is dependent on the free energy, right? Using this formula, this differential formula. Okay, so now after that we have substituted the value of expression of free energy into the pressure equation, and from there after doing the calculation, this would be the formula of the pressure in terms of partition function we have written. That is, we have to do the log of Z, then we have to do the derivative and multiply with kBt. So first doing the log gives us this, then if you do the derivative, we'll plot this. So once again, I think there will be 5 by 2 factor, right? Because there is a t is there, right? T is there. So t is there. So basically, a t is there. So a t is there. So that will be t to the 5 by 2. Now it's correct. Okay. So this would be the final answer we will be getting. So this is the problem number 1. Now we'll go to the problem number 2. Okay. Yeah. So the problem number 2 is in a classical micro canonical ensemble for a system of n interacting particles, the fundamental volume in phase which is regarded as equivalent to 1 microstate is, the options are H to the power n, H to the power 3 into n, H to the power 6 into n. Okay. So before solving this problem, let me just discuss few of the concept in the statistical mechanics. So what is basically an ensemble? So ensemble is basically a collection of all the possible number of states of a system, and each possible states has a certain probability associated with it. Okay. So this is basically nothing but just a mental construction. Okay. So we actually use it to basically represent all the possible configuration that a system can achieve. Okay, all the possible permutation combinations, like energies combination and everything. Okay, at a given certain obviously. So this actually, by doing this mental construction, our mathematics will become very simpler. Okay, that is the reason we are using this concept of ensemble. Okay, so this ensemble we can mentally you can imagine it by just like a single snapshot. Okay, so you can consider like a single snapshot of a system, and this and like every time we're taking a single snapshot, and this all this vast number of collection of this snapshot of the system, that is actually possibly representing the different possible of arrangement of particles, energies and other properties as an ensemble of the system. Okay. So uh, so what is ensemble? So let me just try to figure it out. So ensemble is collection of a large number of possible states of a system. Okay. Which with a certain probability. Okay. So, and each of the each combination has like different possible arrangement of its particle or energies or other thermodynamic functions also. Thermodynamic properties. Okay, so I hope you have understood. So basically, system consists of particle energies and other thermodynamic properties are there. So that system, like there are molecules, like each molecule can have different arrangements, right? And based upon that, the energy can be different. So all of these arrangements for a particular system can be different, right? So all of these different arrangements can be thought as an ensemble of the system. Okay. So why is ensemble is important? So we have used this ensemble knowledge, but what's its significance is? So what happens? So basically, when you deal with a real system, there are like many numbers of particles are there. Okay, enormous numbers of particles. So like it's kind of impossible for us to basically track down the individual, like if there are thousand or millions or billions of particles are there, so it's basically impossible for you to track the individual equation of motion of each particles, and from that you cannot simply able to calculate the state or thermodynamic properties of the system. So for that constraint that we have right now, to solve that constraint, we are coming up with this ensemble concept. Okay, so this ensemble concept basically gives us one statistical prediction. Okay, so this basically allow us to use the statistical methods to predict the macroscopic behavior of a system. Okay, like macroscopic behavior means like temperature, pressure. These are the basically the macroscopic properties of a system, which like should also depend on the microscopic property of the system. And this we are basically doing without actually knowing any microscopic detail, like exact detail of every particle. Okay. So this is one of the powerful technique of using this ensemble concept. Okay. So importance. So importance of ensemble. Okay. So for a real system, enormous number of particles are there. So ensemble allows us to predict the macroscopic detail Macroscopic determines behavior. Macroscopic behavior of the system. So this is the basically one of the importance of using this concept of ensemble. Okay, so now, so mm. Now there are many types of ensembles there. Okay, but here mostly what we are dealing with, especially in this problem, we are dealing with the microcanonical ensemble. Okay, so microcanonical. So what does speciality of this ensemble? So this basically represents an isolated system with fixed energy E particle number N and volume V. So what does that mean? This means that each of the ensemble of the system has a fixed amount of energy, number of particles, and amount of volume. Okay, so let's suppose there are many ensembles, N1, V1, T1, N2, V2, E2, N3, V3, E3, NK, VK, E3. So all of this possible combination of number of particles, volume and energy, which are fixed actually, which is not fluctuating. Like it's not like taking particles from our surroundings or taking energy from surroundings. That is not happening basically. So that's why it's called like it's isolated. So if these three things are constant, and these are basically the ensemble of snapshot of ensemble, or you can say the snapshot of the system for different configuration. So these are basically the ensembles. Okay. And this, if this NV is conserved, okay, it's like remain conserved, then it is known as a microcanonical ensemble. Okay. So now in our problem, says that in a classical microcanonical ensemble for system typing particles, the fundamental volume in phase, which is regarded as equivalent to what microstate is which one. Okay, so so if you want to study, so what is this volume, fundamental volume in phase, which is regarded as, so what is this phase, what this phase is actually meaning? Okay, so so let's suppose if a particle is there moving in 3D. Okay, so it's we can it's if it's in 3D. Okay, so that's one. So we can like in a 3D plane. Okay, in a 3D Cartesian plane we can like we can represent in this Cartesian plane that the particle position and everything, many properties we can like describe, right, using a Cartesian plane, 3D plane. Okay. But here in this problem, the system, let's suppose, let's consider the system, the 3D system. In our problem, 3D system. So that means each particle can have 3 degrees of freedom. Okay, and n non-interacting. So this is basically a 3D system, and n numbers of non-interacting particles are there. Okay, so this means that we can consider a space which is known as a phase space. Okay, so for a system, that is in 3D and has n particles. Okay, so we can represent its configuration in a phase that is called a phase space. That is, phase space is nothing by the space which represents both its coordinates and the momentum. Okay. So for a single particle, one particle, it has three momentum components, right? Components, that is px, py, pz, and three position coordinates, right? Three position coordinates, that is x, y, z. So now if you want to draw the phase space of this one particle, then you have to basically do a 6D space, right? 6D phase space is required. Okay, but in our problem it's not one particle, right? It's n numbers of particle is there, so we basically needs 6n dimensional. Okay, 6n dimensional phase space. Okay, phase space is required. Okay, so so 6n dimensional phase space is required basically to describe the motion of a non-rotating particle in series system, and each of the each each point in this 6n dimensional space, which is called a phase space of the system, basically denotes a microstates of the system. Okay, so now now in the problem we have been asked to find out what is the volume. Okay, now we know that for a we know that in a, like, let's suppose this is a plane, this is a simple plane of x and p. This is also phase plane. Okay. Now smallest volume, that is delta x and delta p in this phase space, we can calculate, right? We have the uncertainty principle, right? From that uncertainty principle, we can basically calculate the smallest delta x and delta p in a phase space. Okay, right? So that is basically nothing but the h curve. Okay, so this is the smallest. Okay, so h curve, right? Now that is in just 2D, right? But in case of a 3D, this like 3D means this is one x direction, one p direction. So this phase space dimension is 2, and if the phase space dimension is 6, that is, so for 2 dimension, this power of h cut is 1 basically, right? So it should be basically, that means 2 is divided by 2, which gives us 1, right? This is basically h cut e power 1, which basically comes from the 2 by 2. Okay, but for 3-dimensional space, for a single particle, there are 3 momentum coordinates plus 3 position coordinates, which gives you 6 dimension, right? And for this case, the partition for this uncertainty principle will be simply gives you delta x delta p by present h cut by 6 by 2, right? Which gives you h cut c, right? So this is for 6-dimensional space. Okay, now we have been asked to calculate for n number of non-interacting particles, right? So for n number of non-interacting particles, this delta x by delta p would be small than equal to h cut 6n by 2, which gives you h cut 3n, right? So, and this is basically the fundamental volume, right? That you have fundamental volume means the smallest volume, and from the uncertainty principle, we already know the smallest volume in this kind of a position momentum space. Delta x delta b should be the minimum limit should be h cut. Okay. So now, using all of these things for a 6n dimensional space, this delta x delta p would be greater than equal to h cut 3. So this would be the fundamental volume. Okay. So what should be the correct answer then? Then the correct answer would be h should be 3. So this is it. So this is how the correct answer is calculated. So let me just discuss it one second what is happening. Okay, so here, so first we have discussed what is an ensemble, basically the different configuration of different possible configuration of a system with certain probabilities. Then we have considered a microcanonical ensemble, which is nothing but like different ensemble of system of a same system configuration with having number, volume and energy as conserved. Okay, so that means there is no interchange of particles or energy with surroundings with all these ensembles. Then it's called a microcanonical ensemble. And in the problem, we have been asked to find out for our n non-interacting particles in a microcanonical ensemble, what is the fundamental phase volume. So what happens here? So phase space is nothing but a space which consists of position and momentum as its axis. So for a 3D system, there are basically 3 position coordinates, 3 momentum coordinates are there. For a single particle, that means the phase space dimension will be 6 dimensional. Okay. But as there are n number of particles are there, which makes the dimension of the system is 6n. Okay. Now we have been asked to find out the fundamental volume. Fundamental volume means the smallest volume. So how can you calculate the smallest volume? So here you already know in a position momentum system in from quantum mechanics that the smallest position and momentum uncertainty that we can have according to quantum mechanics is the product is should be greater than equal to the h cut. So the minimum value it can achieve is the h cut value. Now that is for 2D. 2D means 2D phase space. That means just one position and one momentum, one single component of position, a single component of momentum is there. But for a 6D system, that means this h cut power would be 6 by 2. That made it h cut by 3. H cut to the power 3. Now for our case, as there are n number of non-interacting particles are there, so the phase space dimension will be 6n. And the fundamental volume, that is the delta x by delta p, would be h cut by 6n by 2, that is h cut by 3. This should basically gives the fundamental volume of a phase space. Okay. And if it's a 2D system, let's suppose only x and y is there and px and py is there, then dimensionality will be becomes 4n, right? 4n, 2 position, 2 momentum, which makes 4, and n particles are there, so 4n to n, 4n, and 4n by 2, which gives you 2n. So h to the power 2n was there if it's a 2D system. So now, so this is the problem number 2 we have done. So now comes the problem number 3. So problem number 3. Okay, so problem number 3, let me write it first. So in grand canonical ensemble system made of fixed volume is contact with a large reservoir. B, then what happens? So the option is A can exchange neither energy nor particles with B. Option B is A can exchange both energy and particles with B. Option C is A can exchange only energy with B, and option D is A can exchange only particles with B. Okay. So these are the four options are given, out of which you have to find the correct answers. Okay, so let me screen it. So in the previous problem, we have discussed what does a microcanonical ensemble actually means, right? But in this problem, we are like introduced with a new canonical ensemble, which is known as a grand canonical ensemble. Is so what is basically the definition of a grand canonical ensemble? So in the microcanonical ensemble, we have already discussed. These are like the different configuration of the system. And the characteristics of this microchemical ensemble is it has a particular fixed value of number, volume, and energy that is associated with each ensemble. Okay, and these are constant. So these are constant means what? These are constant means there is basically no transfer of number of particles or energy or volume with the surroundings, which makes them fixed. Okay. This is for microcanonical ensemble, but for grand canonical ensemble, what happens here? So for grand canonical ensemble, uh, the system can basically exchange both the energy and the number of particles. Okay. So that means, so let me just write it. Okay. So for grand canonical ensemble, so the grand canonical ensemble means actually is in contact with a large reservoir that can exchange, one is energy and second is particles. Okay. So contracted from the microcanonical ensemble, grand canonical ensemble can basically exchange both number of particles and energy. Okay, so what are the things that are conserved, like for a grand canonical ensemble? Okay, so for grand canonical ensemble, the conserved quantities are: one is the temperature, second is the temperature T, second is the volume V, and third is the chemical potential. Okay. Name. So these are basically different types of grand canonical ensembles. T1, V1, mu1, T2, V2, mu2, T3, V3, mu3, Tk, Vk, and mu3. So these are basically the grand canonical ensemble of a system. Okay. So in our problem, what we have been asked to find out. So in the problem it's mentioned the system is basically a grand canonical ensemble. Okay. That a system A with a fixed volume is important to consider. So for a grand canonical ensemble, so if it's like connected to a external reservoirs, so what does that mean? It means that it can uh, it can basically allows the system to exchange both the energy and the particles, right? Because that itself is a property of a grand canonical ensemble. If it's a microcanonical ensemble, then it cannot like exchange both the energy or the number of particles with the external reservoir, right? But for grand canonical ensemble, it can basically. That means the answer will be it can exchange energy and number of particles from the reservoir. So this is it. Okay, so this is the correct answer. Okay. So which is option A? Okay, option A is the correct answer. So question number 3 is done. Okay. So we have like discussed about two different types of ensembles, right? One is the classical microcanonical ensemble, and second is the grand canonical ensemble. And so that's it. So now comes question number 4. Okay, so so now comes the problem number 4. Okay. So the problem number 4 is what is the fraction of O2, the oxygen, molecules in nuclear and mu1 vibrational states at 383 Kelvin. For theta V, there is the effective temperature. for vibrational frequency theta wave of O2. So theta vibration of O2 is given actually in the problem. O2 is 3,683 kV. The options are option A 66.6 centimeter, whereas option B 0.3 and option C 6.66 and option D 6.66 centimeter. Okay, so these are the four options are given. Okay, so now uh, hmm, hmm. Okay, so I have to calculate the probability of fraction of molecules in nu 0 and nu 1. So how do we do that? So okay, so we already know, right? If there are like different energy states are there, one like 1, 2, 0, 1, 2, 3, 4. Okay, these types of energy states are there. So probability of being in a state EI would be simply e to the power EI by kBT by Z, where Z is the partition factor. It means summation over all of the possible combinations. So this you already knew, right? So now here's the so here's the vibrational motion is there. Okay. So for a diatomic molecule, you can consider this energy as a simple harmonic motion, right? So we can consider like for a vibrational, like this system is vibrating, right? So all of the energy levels, we can write the energy of this individual energy levels as E nu equal to nu plus half. We can approximate as a simple harmonic oscillator, which is this. So you can write it like this, right? H cut omega. Okay. So now okay, so this is represented. So now here nu can take value, you already know, 0, 1, 2, like this. H is we know that the H cut is nothing H by 2 pi, which is the H is what is the Planck's constant, right? And nu is the vibrational frequency. These are the vibrational frequency. So now, and one more important thing to note here. So and here the vibrational temperature, definition of this vibrational temperature is theta vibrational is nothing but H cut omega by K. K is the Boltzmann constant. This is the basically value of the vibrational temperature of theta wave vibrational. Okay. So if we substitute this thing here, which will gives us the expression, the rewritten expression is H nu is equal to nu plus half H cut omega. You can write is like K into theta v, right? So K into theta v. Okay. Now if we so we knew the energy, right? So now, so first thing, this probability. So in order to calculate the fractions of molecules, basically that means you have to calculate the probability, right? From the n numbers of particles are there, and we know the there are energy states, and if you calculate the probability of of uh, of a particle to be in a state to be in a specific energy state, then from that probability we can calculate the fraction of the particles that can be a fraction from the in numbers of particles that can be into that energy state I. You can easily calculate, right? That basically concludes that first you have to calculate the probability, right? From that probability you can basically calculate the fraction of particles, okay, that can obey that probability. Okay, so basically, so in order to calculate this probability, as we have already discussed, you first have to calculate the partition function, right? So partition function is defined as z equal to summation of exponential e nu by kbt all over the nu. Okay, so this will be simply summation of exponential nu plus half theta v by kb will cancel, theta v by t will be there. So now there's a manipulative symbol. Okay, so this what does this give? This basically gives us if you do the summation, infinite series, infinite geometry series is there. This basically gives you 1 minus exponential of theta minus 1 by 3 whole to the power minus 1. So that basically gives the partition function, right? This is nothing but an infinite series. I will be 0 to infinite. So this is basically infinite geometry series, and we can know the for infinite geometry series, this is the expression, okay, the summation expression, summation value. So this is basically gives us the partition function. Okay, so now this gives us the partition function. Now if you want to know the partition function, you can calculate the at a specific energy, right? So specific energy E nu would be simply so it would be e to the power e nu by kt by z, which gives you e to the power e nu by kbt by z is nothing but 1 minus e to the power. So this we can also write in terms of theta vibration, right? So this will be minus nu plus half theta v by t. So also this one also can write it by same way. So this will be e to the power minus theta v by t. So now, as new value can be become very high, okay, for this kind of system, so because temperature is very high, so you can easily neglect this half factor, right? And you can write it like e to the power nu v by t minus 1 by t. Okay. So now okay. So now, now we have to calculate the PE0. Now from here we have to first calculate PE0, then PE1. Okay. So the ratio of the PE0 by PE1 basically gives you N0 by N1. N0 is the number of particles that should be in that should be in zeroth state, and number of particles that should be in state 1. Okay. Let me write it like this. Okay. So the fraction of, let's say the fraction of, what fraction of nu 0 and nu 1. Okay, so you can write it like this: P of u1 by P of e0, which gives you basically n1 by n0. It basically gives you e to the power minus theta v by t, when e to the power 0 into theta v by t. So this will give you 1. So okay, so but in our problem we are not calculating this. We are calculating just the PE1. Okay, PE1 means PE1 means n1 by n. So fraction of particles that will be state 1 compared to the n is the total number of particles. So that should be just exponential minus 1 into 3 by q. Q means is z. 1 minus e to the power minus theta v by t. Now if we substitute all of this thing, e of p0 e to the power minus 3683 by 383, q is nothing but the 1 minus e to the power 3683 by same thing. So this basically gives you this quantity basically gives you 0.0 do the calculation here. 0.030 40666 by 1 minus this one 0.000 666, which is equivalent to 0.0000666. Okay, so the answer will be 6.66 into 10 to the power minus 5. Okay, which is nothing but the option D, right? Yeah, option D is the correct answer. This will be the probability of particle into energy state 1. So I hope all of you understood how to solve this problem, right? So you have to basically calculate what is the fraction of oxygen molecules in state mu0 and mu1, vibrational states at temperature 383 Kelvin, and theta vibrational is already given. Okay, so these are the states. So first I have written down all the states. So mu0, mu1, mu3, mu1, like this. And this is the probability of each ith state, and z is the partition function of it. So now theta vibrational is this. So we write the energy expression in terms of theta vibrational, which is this. And now we have first calculate the whole partition function z. So z in terms of this energy function mu plus of theta v. So now after doing all of this, we get the partition function, and from there we have calculated the probability of being each in state in E nu. So from there we have first calculate the probability of being state E1, that is nothing but the n1 by n. So that probability basically gives you the number of particles to be in the state 1. So n1 by n, which is basically given by this formula, and we have substituted the value of being equal to 1. After doing all of the algebra, this is the value we get. So this is the way to solve the problem number 4. Okay, so problem number 4 is done. Now problem number 5. Problem number 5 is the value of molecular partition function of CO gas for rotation at 42,000 Kelvin is 16.04. What is the value of the characteristic rotation temperature theta r? And the options are option A 130.92 Kelvin, option B is 261.25 Kelvin, option C is 76.85 Kelvin, option D is 136.94. Okay, so this is the problem. So now problem number 5. So for a rigid rotor, we know for this kind of molecular system which can rotate, more than one molecules are like attached with each other. This kind of rigid rotor, you can know the rotational energy level. So for a diatomic case, let's suppose CO is anywhere a diatomic molecule. So for a diatomic molecule like CO, okay, the energy levels is driven by EJ, that is H bar square 8 pi square I by J into J plus 1. That is B J into J plus 1, where J is the rotational quantum number. So and B is the rotational constant, and value of B is given by H bar square 8 pi square I, and theta is E by KB, which is h square is by q. Theta is nothing but that rotation characteristics rotational temperature. Okay. Yeah, like this rotation temperature. These are the basic like few constants and other concepts. Okay, so now for this kind of system, the so for this kind of system, uh, mm, the partition function, you can write it like this. Partition function only know, right? This is simply v power minus mm, nr e to the power minus er by kv3. So what is this nr terms is coming? This is nothing but the degeneracy of each energy state R. Okay, degeneracy of energy state R. Okay. So this previously in the formulation of partition function, we have never mentioned about this energy because during solving this problem, this concept of degeneracy was not required at that time. So that's why we just ignored this degeneracy term. But if you want to write a general partition function formula, then this degeneration term should be there because each of the energy level can splits into different levels, right? Having same energy value. So that means that energy level now becomes as a degenerate energy level, right? So if a energy state R is having inner numbers of degenerate individual energy levels, then the degeneracy value will be enough. Okay. So if we consider the degeneracy into our formula, then the partition function will be modified into this. Okay. This is basically the formula partition function. Okay. Now here now for this rigid rotor problem, this molecular problem, this formula will be modified into 2j plus 1 e to the power ej per kdt. This is the now the modified partition function, but this is basically is the degeneration. D degeneration of energy level J. This is basically degeneration of energy level J. So now comes now for the case. Now here the case is the temperature of the system is much higher actually. If you can see here, the temperature scale is like 40 to 100 Kelvin, which is literally very high temperature. Okay. Now for this kind of temperature, this formula of this partition function can be approximated as ZR Z equal to simply you can write this with T by theta. Okay. This is approximate case when T is very high. So this would be the Z in case if T is very high. So now so in the problem the partition function, so this value of the partition function and the temperature at which this molecule retains this partition function is given. So now you have to calculate the theta. So theta, then you can write theta is T by Z T is already 4200 and Z is 16.04. If you calculate, you will get roughly this 261.85 actually. 261.85 Kelvin, which is this result. So this is how basically you have to solve this problem. Okay, so what we have done here. So for a diatomic molecule, we have carbon monoxide. So here the first you have written the partition function formula, right? And here you use this more general format of this partition function formula, where the degeneracy term is there. And for this kind of diatomic molecule, the partition function is the degeneracy term of the partition function is 2j plus 1, because each energy state, rotational energy state J has 2j plus 1 numbers of degeneracy. So we have to consider that fact into account, and this would be the expression of the partition function we will be getting. And but in our problem, as you can see, the temperature is 4200 Kelvin, which is very high. Okay, very high temperature. Now in very high temperature, this value of this partition function can be approximated as T by theta. But theta is, we already discussed, is nothing but a characteristic rotational temperature. Okay, so this is the expression, modified expression for high temperature case that we will be using. And all the values are given, like the temperature and the partition function value at which this at the temperature, at that given temperature. So from there, just substitute that thing and we will be getting the theta. Okay. It is 261.85. So this is how we will be solving the fourth problem. Sorry, fifth problem. Okay. So now comes the problem number 5 is done. Now we will do the problem number 6. Okay. So problem number 6. So the problem number 6 is, it's a similar kind of a problem like the previous to previous problem is. So question number 6 is, what is the fraction of N2, that is gas, molecules in equal to 0 and equal to 1. Vibrational states at 453 Kelvin. Okay. So, and theta y, that is theta v for N2 gas is 3240 Kelvin. The option is 7.85 into 10 to the minus 4. Option B is 78.5 into 10 to the minus 4. Option C is 6.66 into 10 to the minus 5, and option D is 0.78 into 10 to the minus 4. These are the 4 options are given. So from here you have to calculate what are the fraction of N2. So here you have to use the same concept. Okay. like what we have done earlier. Okay. So now here also, uh, so let's suppose that two energy states are there. So nu equal to 1 and nu equal to 0. Now we have done in the previous problem already done that p equal to nu equal to 1, the probability is e to the power nu e to the power, sorry, this is sorry this is first one. Or this is power this what we have done to the power e nu, so e nu. So e to the power e 1 by kbt by z, and for p equal to nu equal to 0 was e to the power e0 by kbt by z. So now here the if suppose n is the total particle, n1 is equal to 1, n0 is equal to 0, number of particles is 0, number of particles. So n equal to 0, particles are equal to 0, particles are equal to 1. So this is given, right? So now so this is basically nothing but n1 by n0 is nothing but p is equal to 1 by p equal to 0, and which is n1, sorry, n1 by n0, this simply gives you e to the power e0 by abt. E1 E0 you already know. Okay, that is that is 1 minus 0 by kd theta r by t, right? And 1 by epsilon. So it gives you e to the power minus kd. So kd will cancel. So e to the minus theta by t n1 by n0. So this gives you n1 by n0 equal to this gives you n1 by n0 equal to power minus 32.40 by, that is the 32.40 is nothing but the theta vibrational, and energy is 453. Okay, 3240 and round theta vibrational, and temperature is 453. So 453 is temperature, so e to the power minus, the value will be 7.15 n1 by n0, which approximately gives you 7.85 into 10 to the power minus 4. So the correct answer will be this. Okay, so students, in order to solve this problem, like the formula you already knew, similar, like two states are there, what is the fraction of particles? So the similar formula that we have calculated in the previous problem, starting from the partition function itself, we use the similar formula to calculate the similar fraction of the particle. So that's it. So problem numbers, all the problems of the assignment is done. but we still have some time left, so we can discuss some of the extra problems. Okay. Extra problems. One or two maybe extra problems we'll be discussing. So once again, sharing the stopped. Okay. So as we got some extra time, so we'll discuss some problems. This outside this tutorial. Okay. So okay. So the first problem that we will discuss here is on a two-state problem. Okay. So let's suppose uh, there are two energy levels are there. Okay. One, two. One is having energy value E0, which is 0, and E1 is just simply E1. Okay. Now, for this case, you have been asked to find out a partition function. How can you do this? This is very simply easy, right? So, Z is nothing but the summation of I or on all of the e to the power beta ti. Okay. Now, now for this kind of problem, so there is only two states. Only let's suppose there is only one particle is there. Okay. So it's either can be in zero state or can be E1 state. Okay. So Z will be simply e to the power beta into 0 plus e to the power minus beta into E1. Okay. So Z will be e to the power 0 plus e to the power beta E1. So 1 plus e to the power beta E1. Okay. So this would be the partition function we will get here. Okay, so this is it. So now this is the partition function problem. Okay, one partition function problem. Now let's suppose in the same problem there are two similar states is there. Now we have been asked to calculate like this. It's suppose E0 is 0 and E1 is epsilon. Okay. Now for this system, calculate, sorry, right, calculate the expectation value of the energy. Now when this kind of things is asked, like the expectation value of energy, so this actually means expectation value of the energy actually means that you have to basically calculate the average value of energy, right? Now for this type of problem, you already know the Z is this. So Z you already know, this is this 1 plus e to the power beta epsilon. Okay. Now from this, we already know the right the expectation value of energy. E bar, the expectation is nothing but del beta of ln z. Okay. Now how you can do that? So ln z is nothing but ln 1 minus 1 plus e to the power beta n. Okay, so now with that in our hand, if you do the derivative, del beta of ln z, that is nothing but del beta of ln 1 plus e to the power minus beta e. Okay, now if you simply do the derivative, so what will come first? 1 plus e to the power beta e will go to the denominator, then e to the power minus beta e into beta minus beta. Is there? So, sorry, due to the derivatives minus e, so it's minus e. So, average energy E is epsilon e to the power minus beta 1 plus e to the power minus beta. This would be the average energy of the system. Okay. So this is it. So this is the correct option. Okay. So this is how you can calculate the average energy. For this is a two-step system. Even like similar way, there is a three-state system. Similar way, you can do the same like partition function of a three-state system, and you also can calculate the average energy. Now, if instead of a two states, one particle system, let's suppose there is a two particle system or three particle system. What can be the configuration? So let's suppose there are two particles are there instead of one particle. So two particles are there and three states are there. Okay, let's suppose three states are there. Okay. So let's suppose E0 is 0, E1 is epsilon, and E2 is let's suppose it's 2 epsilon, or yeah, 2 epsilon. This is the energy states are given. Okay, so now let's suppose for this system there are two particles. Okay, 1 and 2. Now what are the configurations? So configuration is it's either can be so 1, 2, 3. So it can be this and this. It can be this and this. It can be this and this. Okay. Let's suppose it's a bosonic system. Bosonic means that each state can accommodate more than one particles. Okay, so that it doesn't have any uncertain like exclusion principle. Okay, in Fermi system we have an exclusion principle, right? Like two particles in same quantum number cannot occupy a single state, right? Two particles in same quantum number. Okay, but here that is a Fermi system, but here let's consider it as a bosonic system. Okay, so That means like this is a configuration, this is a configuration, and this is also configuration. So epsilon is 1. So here Z is basically, so Z we know I e to the power beta epsilon. So here the case is e to the power minus beta epsilon. Here it's would be 1 plus so here the combination is 1 plus e to the power minus beta epsilon, where is 1 plus e to the power beta epsilon. Here it is 1 plus e to the power beta epsilon plus e to the power minus 2 beta epsilon. This case, for this case, it will be 2 into e to the power beta epsilon. For this case, 2 into e to the power beta epsilon. Here in this case it will be simply 2. Okay. So if we write all of these common combinations, the total Z will be 1 plus e to the power beta epsilon plus 1 plus e to the power 2 beta epsilon plus e to the power beta epsilon plus minus 2 beta epsilon plus 2 e to the power beta epsilon plus 2 e to the power beta epsilon plus 2. So it would be 3, sorry, 4, so 1, 2, 3, sorry, so this is 1, 2, so 4 is there, right? So 4 beta epsilon, 2 beta epsilon also be 4, I think, and this, yeah, 4 will be 4. Something like that. Yeah, I guess it's fine, correct, okay. So this would be all the possible combinations, right, that we will be getting. So okay, so that's it. Okay, so this should be the final partition function we'll be getting. Okay, now from this partition function, in similar way you can calculate like different quantities. Like here we have calculated the average energy. Okay, now similar way, right, you can also calculate the free energy also. Right? Free energy we know already, this is A, B, T, L and Z you already know, right? So Z was like 1 plus e to the power minus beta epsilon. So A, B, T will like 1 plus e to the power beta epsilon. So this is also free energy. So from free energy, like previous problem was also discussed, like for free energy you can calculate other items like pressure, entropy, temperature, all of these things. So this is it. Okay, so this is, so in this tutorial basically we have discussed some very key concepts around partition functions and how basically we can use this partition function like in order to solve different problems, and also how can you use the partition function to like derive many kinds of equilibrium equilibrium thermodynamics properties of the system like pressure, temperature, volume and all. So that's it for today's class. I hope all of you like understood. So thanks for